Hello and welcome to the second lesson for Unit 7A, Differentiation. This is Lesson 2 about differentiating functions. Firstly, we need to understand how to write our functions. This is known as function notation. You will already be used to the way that we write functions in two variables, usually x and y. For example, y is equal to 3x plus 2. This simply means that we take x as an input, multiply it by 3, and then add 2, and that gives us our answer for y. So we have inputs x and outputs y. This means that y is a function of x, and you should familiarize yourselves with an alternative notation. This notation is f of x equals 3x plus 2. It is the same function, but it is notated as a function of x, with f brackets x. It simply means f is a function of x. Usually we start with f and other functions are g, h, etc. The two notations should not be mixed within the scope of a question, as this becomes confusing. Throughout this presentation, alternative notations will be used. Now we need to understand how to write out our differentiation. When we differentiate, what we are trying to do is find the gradient function of an original function. That will allow us to find the gradient at any point along the line. If we now consider that the gradient at any point is represented by a small change in y divided by a small change in x, then our delta y divided by delta x becomes dy by dx, where dx and dy just mean a very small change in x and y. This will allow us to have the gradient at any point. So when we're differentiating y, this is how we write it. D by dx of y, which is the function, is equal to dy by dx, which will be the gradient function. This is called Leibniz notation, after Gottfried Wilhelm Leibniz. More information can be found on the link. When we are using the alternative function notation, f of x, differentiation is then represented simply with an apostrophe. So the differential of x will become f dash of x. This is called Lagrange notation after Joseph Louis Lagrange. More information can be found on the link. It's very important to note that you should never write an equal sign between a function and its derivative, as they are not equal. Let's have a look at some examples of differentiation using both the Lagrange notation and the Leibniz notation. The Leibniz notation will be on the left and the Lagrange on the right. Our function is going to be 3x plus 2. With our standard notation that we're used to, we can let y be our function. So y is 3x plus 2. With Lagrange, we call this f of x. The function of x is equal to 3x plus 2. Now when we differentiate this is how we write it. The Leibniz notation, we will have d by dx of y, which gives us dy by dx is equal to 3. For the Lagrange, it's simply f dash of x is equal to 3. We will come on to how we find these values later. If we differentiate again, you will note that the Leibniz notation was still applying a d by dx of our dy by dx already. So therefore, we'll get d squared y by dx squared. In this case, this will equal to 0. With Lagrange notation, simply we just add another apostrophe. So it just becomes f dash dash or f double dash of x. In this case, again, it equals 0. You should write out the notation exactly like this. Let's now look at how we differentiate actual functions. To start with, we're going to be looking at polynomial functions, which are simply just powers of x. The general rule for differentiating a polynomial of x, firstly, write out the powers of x, including 1 and 0. Secondly, multiply by the power of x in each case. Lastly, reduce the power of x in each case by 1. In general terms, this is shown below. So we have d by dx of a function, which is represented by a times x to the power of n. A is just a number and n is just a number. When we differentiate this, we simply take our n and we multiply it by the function. So we have a times n, and then we reduce the x power by 1. So that becomes then x to the power of n minus 1. Let's have a look at an example here. If we have a function here, y is equal to 2x cubed minus x squared plus 4x minus 7. We're going to be differentiating with respect to x, which is what you might see in some questions. So we're going to be reducing the powers of x. So firstly, we do step 1, which is to show the powers of x. Writing this out has been highlighted in red. So now y is 2 times x cubed minus 1 times x squared plus 4 times x to the power of 1 minus 7 times x to the power of 0. You will note that the x to the power of 0 we put in there because the number was just 7. X to the power of 0 is 1. 7 times 1 is 7. Therefore, we can include the x to the power of 0. Now it's easy to differentiate because we just take the power, multiply by the power, and reduce the power by 1 in each case. Let's have a look. So dy by dx becomes 2 times 3x squared, where we've taken the x cubed, we've multiplied by 3 and reduced the power down to 2. The next term, minus 1 times 2x to the power of 1. We've multiplied by the 2 and then we've reduced the power to 1. Plus 4 lots of 1x to the power of 0, where we've taken the power 1, multiplied, and then we've reduced the power to 0. And then lastly, minus 7 lots of 0, because when we multiply by the power of 0, we will get 0. The last step then is just to simplify. The 2 times 3 becomes 6x squared. 1 times 2 becomes 2x to the power of 1 is just x, plus 4 times 1x to the power of 0, which is just 1, so it's 4. You should write the notation and lay out your work exactly like this. We're now going to look at some examples of functions from the previous lesson. The function that we have here, the line, is y is equal to 2x minus 1. We've already established from the previous lesson how to find the gradient of a line. We take 2 points and divide the change in y, which is 4, by the change in x, which is 2. That gives us a gradient of 2. So when we differentiate, we should be actually looking to see that we get the same answer. Our general rule is shown there below. Taking the power, multiply by the power, and then reduce the power by 1. So firstly, let's show the powers of x. So y is now 2 times x to the power of 1, which is just x, minus 1 times x to the power of 0, which is 1. So when we differentiate, all we do is multiply by the power and reduce the power by 1. So x to the power of 1 becomes 1 times x to the power of 0, which is 1. X to the power of 0 becomes 0. So simply our dy by dx becomes 2 times 1 minus 0, and the answer is 2, confirming what we already knew from when we measured our gradient. In this second example, we have a negative line here with a negative gradient. We have already established what the gradient is from the previous lesson. Let's have a look at how we differentiate it. The function of x in this case is minus 2/3 of x plus 5. It may also be written as 5 minus 2/3 of x. As you can see, if we were to measure this straight line, we get minus 4 divided by 6, which simplifies down to minus 2/3, which is the answer that we're looking for. Now looking at our general rule again, f dash of x, because we're using Lagrange notation this time, of a times x to the power of n becomes a times n, which is the power, times x to the power reduced by 1, n minus 1. So we will be differentiating with respect to x, so show the powers of x in our function. So we have minus 2/3 of x to the power of 1 plus 5 times x to the power of 0. So simply multiply by the power and reduce the power by 1. Our x to the power of 1 becomes 1x to the power of 0. The x to the power of 0 becomes 0. So our function, our f dash of x now, our gradient function, becomes minus 2/3 of times 1 plus 5 times 0, which just leaves us minus 2/3, which confirms the answer that we got from measurement. Let's now have a look at our vertical and horizontal lines. The horizontal line is f, the vertical line, the blue line, is g. The red line f is a function of x, so that f of x is equal to 0.25. As you can see, the horizontal line goes through 0.25, and this is a flat line. We would expect our gradient to come to 0. Let's have a look at what happens when we differentiate. So let's show the powers of x. Well, we know that just a number will be multiplied by 1, which is x to the power of 0, so we can put that in. So f of x becomes 1/4 of x to the power of 0. Now when we differentiate this, we multiply by the power and reduce the power by 1. So multiplying by the power becomes 0. So the answer of f dash of x is 0, confirming what we already said. A gradient of 0 always indicates a flat or horizontal line. G, the vertical line, is not a function of x, and therefore we cannot differentiate it. It will have an undefined gradient. So far, we have just looked at straight lines. You will have noticed that all the answers result in just a simple number. This is because the line is straight and the gradient is therefore the same along the whole length of the line. We now have to consider what happens when we differentiate and find the gradient of a curved line. The first line we're going to look at is shown on the right, which is y is equal to x squared. Or in this case, we're going to be using v is equal to t squared, where t is the horizontal and v is the vertical axis. This is to give an example of showing you how to differentiate with respect to a different variable, t. We'll be differentiating with respect to t. So therefore we're going to rewrite showing the powers of t. So we have v is equal to 1 times t squared. If we're going to differentiate, we need to multiply by the power of t and reduce the power by 1. So we get 1 times 2t to the power of 1. Simply simplifying, this becomes 2t. Notice that this differential function is still a function of t, i.e. it contains the variable t in it. This means that the gradient will actually change along the length of the line according to the value of t. So to find an actual gradient at a point, we need to substitute the value of t into the equation to find the gradient. For example, if we're looking at the point where t is equal to 1, differentiate using the differential dv by dt, we get 2 times t, which is 2 times 1, and the answer is 2. If we were to draw a tangent at the point where t is equal to 1 and measure it, you can see the length of the line is 1 and goes up by 2. Therefore, we have a gradient of 2 divided by 1, which is 2. Let's now look at a more complex function. The curve on the right is a cubic curve. This function is x cubed minus 3x squared plus x minus 1. We want to find the gradient when x is equal to 1 and x is equal to 2. You will see that at the point where the line crosses x equals 1, the curve has actually got a negative gradient. When it crosses the x equals 2, it is then going up and now should have a positive gradient. So therefore we should be expecting those results when we differentiate. So we're going to differentiate with respect to x. So write out the function showing the powers of x. So f of x is 1 times x cubed minus 3 times x squared plus 1 times x to the power of 1 minus 1 times x to the power of 0. Differentiating by multiply by the power of x and reduce the power by 1. So for each term we now have f dash of x is equal to 1 times 3x squared minus 3 times 2x to the power of 1 plus 1 times 1x to the power of 0 minus 1 times 0. Simplifying this will give us 3x squared minus 6x plus 1. So when x is equal to 1, substituting 1 for x, f dash of 1 will equal 3 times 1 squared minus 6 times 1 plus 1. That will give us 3 minus 6 plus 1, which equals minus 2, confirming what we thought already. When x equals 2, f dash of x becomes f dash of 2. Substituting 2 in the equation, we get 3 times 2 squared minus 6 times 2 plus 1. That gives us 12 minus 12 plus 1, which equals 1. If we look at our tangents, we can see that at x equals 1, the line is negative, and x equals 2, the line is positive, as we expected. Now it's time to do some example questions. Differentiate the following functions. Number 1, y is equal to 3x squared minus 2x plus 4. 2, f of x is equal to 3x cubed minus 2x squared. 3, s of t is equal to 5t squared minus 2t plus 2/3. For this equation, you should be differentiating with respect to t, using the correct notation. Equation 4, g of x is equal to 4ax cubed minus 2a cubed x squared plus 6a. To differentiate with respect to x for this function, note that a is just another variable. You will not be differentiating a, and you can ignore it and use it as it was just a number. When you've finished, click Next on the PowerPoint and the answers will be shown. The answer to number 1, dy by dx is equal to 6x minus 2. Just to go through this, we have 3x squared. If we differentiate x squared, we get 2x times 3 becomes 6x. If we differentiate minus 2x, if we differentiate x, we get 1. So minus 2 times 1 becomes minus 2. If we differentiate 4, we get nothing. Question 2. F dash of x is equal to 9x squared minus 4x. If we go through each term, 3x cubed. If we're differentiating the x cubed, that becomes 3x squared. Multiplying by 3, we have 9x squared. The second term, we're differentiating x squared, which becomes 2x, times minus 2 becomes minus 4x. Question 3. S dash of t, as we're using the Lagrange notation, is equal to 10t minus 2. Let's look at each term. 5t squared, when we differentiate t squared, becomes 2t, times 5 is 10t. Minus 2t, when we differentiate t, we get 1, so that therefore becomes minus 2. 2/3, when we differentiate, becomes nothing. Question 4. The answer is g dash of x is equal to 12ax squared minus 4a cubed x. Going through each term, the 4ax cubed, we are only differentiating the x cubed, which becomes 3x squared. Multiply by the 3 by the 4, giving us 12, by the a, 12a, so it becomes 12a x squared. The second term, minus 2a cubed x squared. We're only differentiating the x squared, which becomes 2x. Therefore, multiply the 2 by 2, we get minus 4a cubed x on its own. 6a at the end differentiates to nothing, as it's just a number. Now have a go by yourselves. The worksheet attached has a number of functions which you're to find the gradients given on the worksheet. Ensure that you use the correct notation and show the working as in the examples.